So in the last lecture, we studied how uniform integrability relates to the convergence of random variables in L1. So in this lecture, what we're going to do is to apply those results to sub-martingales and martingales. So this is going to be about uniform integrability and martingales. So the results of this lecture are going to be simple to prove as well, and they will mirror in a certain way what we saw in the last class. So it's not going to be a very technical lecture. The first theorem we're going to prove concerns a submartingale, and it says, just like the theorem we saw in the last lecture, that three statements are equivalent. So the first one is that the family Xn of random variables is uniformly integrable. The second statement says that Xn converges almost surely and in L1. And the third and final statement says simply that Xn converges in L1. So these three statements are equivalent, and you see that it's a very nice result to have, because we saw a previous result about the convergence of martingales, but we couldn't obtain L1 convergence, we just obtained almost sure convergence, and now we have the correct hypothesis to obtain L1 convergence. And when I mean correct, it's because it's an equivalence, right? So it's an if and only if statement. So the proof is going to be very simple. It's going to be heavily based on the previous result we saw. So first you're going to see that 1 implies 2. So uniform integrability is going to imply both almost sure convergence and convergence in L1. So first let's recall that 1, the uniform integrability, is stronger than saying that a family is bounded in L1. So this implies that the family is bounded in L1. So what does that mean? That the expectation of the absolute value of xn is smaller or equal than a constant for every n. So we know that this is a very weak statement when we're talking about arbitrary random variables, but when we are talking about submartingales, this actually implies that xn converges almost surely to some x. Actually, the hypothesis we had in convergence of submartingales theorem is that the expectation of the positive part was uniformly bounded. And here we're getting something even stronger. So this definitely implies that xn converges to x almost surely. So now let's add this. Let's call this 4. So if we go back to 1 and now add 4, you see that we have almost sure convergence and uniform integrability. By the theorem of the next lecture, this implies L1 convergence. So we are finished with 2, because 2 was exactly saying that xn converges in L1 and almost surely. So this is done. And now we're going to it's obvious, of course, that 2 implies 3. 2 is saying that the submartingale converges in L1 and almost surely, while 3 only requests L1 convergence. So this was easy. And now we turn finally to 3 implies 1, which is the final part of the implication. So if something converges in L1, then it also converges in probability. Xn converges, Xn converges to X in probability and in L1. Now, again, it's a result from the previous lecture that if something converges in probability and in L1, then it also converges. Then it's also uniformly integrable. So this finished the theorem. As I said, it's not a very technical result. It's something that follows from a few observations and the theorem from the last lecture. Okay, so now let's use this theorem to study a bit more what's happening with random walks and the heating time of 0. So remember that Xn in a previous lecture was defined as a simple random walk starting at 1. And we know that Xn is going to hit 0 in a finite time almost surely. So if you define the infimum of times such that Xn equals 0, then t is equal to, t is finite almost surely. Not only that, we also saw that x stopped at this random time is again a martingale. And that xn minimum t converges almost surely to 0. So a simple random walk is starting at 1 is going to almost surely hit 0 at some point. And then if we define a new process that once it hits 0 it never leaves again, this process converges almost surely to 0. But another observation is that this new process here, yn defined as xn minimum t, is a martingale. So the expectation of xn never changes. It's equal to the expectation of x0, of y0, which is 1. So it's not true that yn converges in L1 to 0. This is not true because the expectations are not converging. So in particular, this is another example of a family that is not uniformly integrable. So somehow this random walk that is defined by very simple jumps up and down, it's getting more and more difficult to integrate, more and more heavy-tailed up. It's not a family of uniformly integrable random variables. Even if we kill it, if we let it stop after it hits 0, which it does almost surely. Another way to see this is to think about this is to think, okay, it's definitely gonna hit 0, but if we know that it did not hit 0, it's probably very high up. So this is another interpretation of the fact that this apparently very well-behaved process is not uniformly integrable. Okay, so now let's see a result that I find very fascinating that is also related to the L1 convergence of martingales. recall before we go to the theorem, recall that if we had a variable x in L1 and we had a filtration Fn, then Xn defined as the expectation of x given Fn was a martingale. So this example looked like a very particular example, right? So it's something like there is some divine entity, like God knows the future, and you only know the future given what you know up to now, given your information. And this is a martingale. But maybe it's a very particular martingale, right? Maybe it's just a tiny example. What the next theorem is going to say is that this is much by the opposite. It's a very rich example of martingales. Several martingales fall into this definition. So let's see why. So suppose that Xn is a martingale. So up to now it's an arbitrary martingale. It's not something that we are constructing somehow. But we also assume that Xn converges to X in L1. Okay, so we have a process that is a martingale, and the only hypothesis we have is that it converges in L1. Then we can write Xn as a conditional expectation given Fn. So this example that we gave very early in the lecture about martingales, that I like to call the God's martingale, like God knows the limit and you only know the information up to time n. God knows what's going to happen to your life or to your betting, but you only know the conditional expectation. And this is a martingale. This is actually a very general example of martingale. All the martingales that converge in L1 are an instance of this example. So how do we prove this? So it's going to be a proof that is going to make a little trick with the definition of martingale. So what a martingale essentially means is that if m is larger than n, then the expectation of xm given fn is xn. So this is not exactly the definition of martingale. The definition of martingale is the above when m is equal to n plus 1, but you can use an induction and prove the above, that for every m larger than n, the conditional expectation of xm given fn is xn itself. And another way to write this conditional expectation is saying that for every event in fn, the expectation, now not the conditional expectation, the normal expectation of xm is the same as the expectation of xn if we look at events a in fn. So this is essentially the definition of conditional expectation as above. So why is this interesting? We can um, relate the expectation of xm in the event a with the expectation of xn of x, the limit on event a. Why do we want to do this? Because you see, this looks very much like what we want in the end, right? This is what we have, this is what we want. But the difference is that here we are writing xn as the expectation of a future time given fn, and here we want to write expectation of xn as the expectation of the infinite time process given fn. So all we have to do now is relate the large time xm with the infinite time x. So how do we do this? We're gonna, of course, take the absolute value of this difference and bound it by the expectation of the condition of the absolute value. So here you have xm indicator of A minus x indicator of A, and this we can put the expectation, the indicator function outside, and actually bound this just by the expectation of the absolute value. But remember, our hypothesis says that xn converges to x in L1. So this expectation converges to 0 as m goes to infinity. So what we can obtain from this is that let's recall, this thing here is equal to xn. So we also obtained that the expectation of xn, indicator of A, minus the expectation of x, indicator of A, is smaller or equal than this, which goes to 0. So see that on the left here we don't have an m, we only have n. So this is bounded by something that goes to 0 with m, but does not depend on m. So this is actually equal to 0. So now we proved that this is equal to this. But at the same time, this exactly, by the way, for every a in Fn, and this is exactly the definition of the conditional expectation. So xn is equal to the conditional expectation of x given Fn. And we're done with the proof. So this is for the to finish the lecture on the relation to martingales and convergence in L1. And I would like to finish just saying that it, it was a difficult process to try to obtain conditions for L1 convergence, but it's actually an important effort because martingales are all about expectations. It's expectations that define what is a martingale and the main properties of martingales. So it's important to obtain convergence that are not only in L1.